in the idea of a definite interval, we have a definition for it. It's a number J, where J is the limit of the sum. And that's a K there. If so, this is the idea. To put this another way, a definite interval is going to be this. And again, what we're going to do, we're taking some curve, we're approximating the area. Like so. And each area, if we take one of these squares, one of these rectangles, we have a CK, we have an F of CK, it has a width, delta XK, and it has this height, that's the F of CK. So what we're doing with this is we're adding up the areas of each of these rectangles to get the entire area. So I'm doing a little bit of review before I get into the criterion of the if. I'll give you a little bit more time to copy that down. Just going to review a little of this before we get into the if here. You know, this is going to be true if. And the idea is, what is J? Well, J is what we get after taking this limit. So as we take this limit, these rectangles become smaller, but they become more numerous. They will fill in this area under the curve much better. And as a result, now P represents the largest width of one of these rectangles. So as these become more numerous, P has to get smaller and smaller, or as P gets smaller and smaller, we get more rectangles. Or the measure of P, or the width of P, shrinks. What happens is this scenario becomes this scenario. And now we actually have the area. And this is the number J. That's the number J. So this happens if so we'll get back to that if, where we just kind of left everything hanging. Now, what you're going to see is something that we're not going to get into, because you're going to see an epsilon, and you might be thinking, uh-oh, here come those epsilon proofs for limits. Well, we're not going to take it that far. We're going to acknowledge that it exists, and then we're going to move on. If for any epsilon greater than 0, there's delta greater than 0, such that for every partition P, and a partition, if you don't remember what that is, that's just taking the interval AB, where we'll let A be x0, and then we just choose points that break this up into subintervals. So for every partition P, where we break it up into these little, we're going to break it up into subintervals. And again, this is a partition of AB. So every time we do this, where the width of the largest subinterval, that's what this stands for, the largest subinterval, that is less than delta, and any put it for any CK in, and there's like one of these little subintervals. You can have something like this. So the idea is that you're going to pick an epsilon, some arbitrarily small number, and then that means for that small number, there's going to be some delta where for every partition of this interval AB, this is where we're doing the integral on, where the width of the largest interval, subinterval, is less than delta, then the difference between our sum, our approximation of this area, and the true area is less than that epsilon. So this is a way of expressing that limit. It's a very formal way of doing it. So what is this actually saying? Well, what we're saying is this. When we talked about these approximations of areas before. And what we're actually dealing with these approximations of areas, they're really what's called a definite integral. We talked about indefinite integrals, and those are another way of talking about those is those are antiderivatives. What's the opposite of a derivative? Well, it's going to be your antiderivative. What function did your derivative come from? Well, that's your antiderivative. So what we're talking about with the definite integral is actually the areas underneath these curves. So this gives us the area underneath a curve from A to B. And this is now going to become our definite integral from A to B, f of x dx. That's where we're going with this. So any questions about that? So I'm just going to kind of review what's going on in this process. So I kind of get on the same page, and then that should be, for the most part, the last of the theory. And I know the theory can get a little heavy, but then we'll be done with that, and then we'll be pretty much into computational things for the rest of the semester. But bear with me a little bit. So let's note something here. For the number in of rectangles as p goes to 0, we have n going to infinity. So to illustrate this, and just to kind of, I know it's been a little bit since we've talked about partitions. So here's, say, A equals 0, B equals 1. And let's take a partition, say, let's take 1/8, 1/2, and let's go 7/8. So this means our partition will be 0, 1/8, 1/2, 7/8, and 1. So what about the width of our partition? Well, we want to find the distance between these points, because when you put these points on the x-axis, these create subintervals. So taking a look, distance between these is, well, 1/8. Yeah, it's kind of hard to see. Try this. Let me make a little bit of room here. Let's take a look at this one. What's the difference between these? Well, let's find out. You've got 7/8 minus 4/8. That's going to be 3/8. And then 4/8 minus 2/8 is 2/8, or 1/4. We'll just call it 2/8. Keep all of our denominators the same. And this is 1/8. So the width, the biggest subinterval, is the one from 1/2 to 7/8. So that means the measure of P here is going to be 3/8. So that's this idea with partitions. Now, what we typically do is we typically pick points for our partitions. So the width of the subintervals, that these widths are all going to be the same. But you don't have to do that. You could just choose points fairly randomly along here to come up with a pretty random partition. And that's kind of one of the power of this definition, is that we don't have to use intervals that are the same size. We can use intervals that are different sizes. But regardless, here's the thing. If we take the biggest one and we make this go to 0, then certainly as this width gets smaller and smaller, all these other widths will get smaller and smaller. So that's kind of the idea here. The width of the other subintervals are going to shrink. So questions about that? We're going to do a kind of a quick picture of what that looks like. All right. If I'm going too fast, let me know. I'm erasing things too quickly. So the idea is going to be this. We just saw it written as this largest width goes to 0, the number of rectangles goes to infinity. For A or B, there's B equals 1, A equals 0. And so now what we're going to get is a rectangle that's just almost infinitely narrow. We have our areas. And let's say this is our biggest interval with the width going to 0. So these are just going to get smaller and smaller until we can just pack them in underneath this curve. And that's going to give us that area that we call J when we add up all these little rectangles. So recall, now we're getting back to our Riemann sum. Delta xk. Now we did go with a fixed width delta xk. We actually did do that. And then we said ck would be a plus multiples of delta xk. So what this is going to mean, now the key thing here, as this goes to 0, the number of rectangles is going to grow infinitely. So we're just going to rewrite our limit. And instead of using it in terms of a partition width, or the width of the largest subinterval in a partition becoming smaller, making all the other ones become smaller, and that causes more rectangles to be needed to fill in the area. Instead, we're just going to say this: as the number of rectangles that fill in the area grows to infinity, we're going to get our area. So the limit, as the width of the largest interval, subinterval, goes to 0, fck delta xk, this will become the limit as n goes to infinity. And here we get a very specific formula for calculating our definite integral. And so this is what we're going to mean. F of x dx. So any questions about that? All right. So depending on the choice of CK, we can get a lower sum or an upper sum. So a lower sum we choose CK. So F of CK is smallest value of F on a given subinterval. So the idea is that there's different, you can choose your FCK. Now, the way we've chosen it, the formula that we're working with is going to give us a CK that's always going to be the rightmost point of our subinterval. And that's what we're looking at in this section. But there's other things you can do. I'm just going to check something here. Real quick. Sorry, I was consulting a different textbook on something real quick there. Now, an upper sum we can choose CK. So F of CK is the largest value of f on the subinterval that you draw ck from. Now, we're going to talk about when something is an integrable function, and the idea of upper and lower sum, this actually comes up. And we're testing for integrability, and I'm not going to get into that too much. There's a great example in the text here, and I'll put a page number for it, but it's going to be on page 302. For the sake of time, I'm going to skip it, but it goes over when a function is not going to be integrable, which might sound kind of strange, but can you have something where you're not able to come up with you're not going to be able to come up with an integral for this definition. But what we're talking about here, like let's say we have something like this. So we could say we have this value, we have this value, and we could call this UCK. So this value on an interval, we'll call this xk minus 1, and we'll call this xk. And this is where you would use for the lower sum. CK, in this case, would be xk. And it doesn't have to appear at the endpoints. These could be occurring in the middle as well. At this point, you could use as an upper sum. And here CK would be xk minus 1. The significance of these two, and again, this is for that example on page 302, is that you can use these to show when an integral doesn't exist. That's the key significance with these two. Oh, I'm sorry, I didn't have that showing. You can use these to show when an integral doesn't exist. And we're going to talk about real quickly, sort of our last little piece of theory, just mention about whether or not something is going to be integrable or not. And it's going to, and just like with derivatives, you're going to, one of the key issues is going to be continuity. That's one of the big things in this. But again, this lower and upper sum, that's going to be helpful if you ever need to show something is not integrable. So these can be used to show if a function is not integrable. And so, and part of the issue is that the example on page 302, it's not continuous, for one. The idea is going to be this. When you choose an upper sum or a lower sum, you're choosing different CKs. Now, if an integral does exist, it doesn't matter what you choose for the CKs. It shouldn't matter. So the integral exists if our limit value, that's that big limit for the sum, does not depend on choice of the CKs. So this is sort of something to throw out there. If you want to check out that example, I do recommend it. But for the sake of time, I'm just going to have to move forward into the meat of things here. Here's our theorem. This kind of brings us to head. If f is continuous, on AB, or has at most finitely many jump discontinuities, then integral from A to B of f of x dx exists, and f is integrable on AB. So questions about that? So just to not confuse things, I think I will. It's kind of pressing on time. I think I better just go forward. I would like to do the example, but we're running low on time. But basically, what this is going to give you is that basically, of a function that has a finite number of jump discontinuities, then you can still integrate it. Continuities like if you're trying to integrate 1 over x from -1 to 1, you're going to have that vertical asymptote. And 1 over x is not going to be integrable. The function they're talking about in this example, what they're kind of getting at is, I'll go over just a bit, because this is all being a little too mysterious. You have a function defined as such, and this does not have finitely many discontinuities. It has infinitely many. And it's going to be equal to 1 if x is irrational. And it's going to be 0 if x is rational. And so the idea is that you'll integrate this over 0, 1. And let's say you come up with a partition. So we could say, like, we could let delta xk equal b minus a over n, or 1 minus 0 over n, or 1 over n. So you're going to take 0, 1, and you're going to partition it into these subintervals. And you're going to get something like this. So here's the thing. If we take a particular subinterval, let's take xk minus 1, xk. If ck is irrational, then f of ck equals 1. But if we choose an f of ck is a rational number, then f of ck is equal to 0. So what we're going to do is this. I know this is pretty theoretical, but if we think back to our definition for our indefinite integral, it doesn't matter which partition we choose, what kind of partition we choose, or what kind of ck's we end up choosing. Those partitions, as we let n go to 0, I'm sorry, n go to infinity, we're going to get the same number for our limits. So we're going to choose two different sets. Of ck. And this is where those upper and lower sums come in. The upper sum we're going to get f of ck times delta xk, where this is always going to be equal to 1. Because we're going to choose ck to be irrational. So any questions about that before I go forward? So that's going to turn this sum. We're going to call it an upper sum because it's going to turn out to be the bigger sum. K equals 1 to n of 1 times, and then our delta xk is 1 over n, which this is a constant, n's a constant, so this pulls through of 1. So we're adding 1 up n times. Oh, sorry, let me lower that down. So we get 1 over n times n, or 1. So one of these upper sums is, we're going to get 1. Now for a lower sum. So for this one, this one's going to be 0. We're going to choose the smaller value of f, since we're going to let ck be rational. And so since we're multiplying by 0, we're just going to get 0. So what we get is the upper sum equals 1 for any number n, and then L is going to be 0 for any number n. So what this is ultimately saying is that the limits are depending on the choice of ck. So this means the integral doesn't exist. I want to put this in parentheses. It's the Riemann integral. And I do want to mention that there are some functions that you cannot compute a Riemann integral for. Oh, sorry. You cannot compute a Riemann integral for, but you can actually compute a different type of integral. You can actually do that. So there are some functions where you can do that. Anyway, I just want to go through an example to illustrate why they're bringing in these upper and lower sums. And if you take math in the future, if you take what's a course called analysis, this comes up. You can actually use these quite a bit, depending on which textbook you're using. So another reason to bring them up. Anyway. All right. So let's get into some hard, just kind of hardcore, like this is just hands-on type stuff. We got a little bit, not pretty much we're through the theory. So let's take a look at some properties. So if we integrate f of x dx, and if we switch the order on the integration, we get a negative sign. If we have a lower bound and an upper bound that are the same, in other words, it's a rectangle that has a width of a point, well, that's going to be 0. And then you're going to see some properties that are similar to those with derivatives. Now, we don't have a product rule. We don't have a quotient rule. But we do have something like this, where k is a constant. K will pass through the integral sign. So again, like with derivatives, the integral of a sum or difference, it will be the sum or difference of the integrals. And then you can break up integrals in the sections. So any questions so far? Another property, if f of x is continuous, oh, I'm sorry, not continuous, f of x has a minimum and a maximum, value on AB then the minimum of f times b minus a is less than or equal to the integral of f of x dx over that same interval, which will be less than or equal to the maximum of f times b minus a. Now for f, so these are just more properties. For f of x greater than or equal to g of x, on AB this implies that the integral from A to B of f of x dx is greater than or equal to the integral A to B g of x dx. And there's a property similar to this. If f of x is greater than or equal to 0 on AB, then the integral from A to B of f of x dx is greater than or equal to 0. We're almost done. One more property. We get to jump into some examples, do some calculations. So any questions about these? All right. And so finally, if f of x is non-negative, and integrable on AB, then the area under f of x over that interval AB, so between f of x and the x-axis along AB. And this is what we've been pretty much talking about the whole time. Area is going to be this. And we'll talk about what to do when the function is not always positive, when it's negative. We'll get to that also. But those are going to be the properties of our definite integrals. And you can think of them, if it helps to try to understand what these properties are saying, you can think of them in terms of areas of functions, areas between the function and the x-axis from A to B. And some of these rules might make a little more sense, or they might kind of get a picture of what's going on. But we're going to be working with this one here. We're going to be talking about this for some of these examples. So let's say we have this. Find the integral of f of x equals x from A to B. And so this is going to be a bit abstract. We're going to sort of, in the way this is sort of like with what we did with derivatives, like finding the derivative of x to the n. We found it's n times x with an exponent of n minus 1. We're sort of doing that kind of a thing. Let's say we have this, though. Draw a picture, see what's going on. So here's f of x equals x. So what we want to do, so this is the area we're looking for. Well, what we can do is we can break this area up. There's our A. Here's our B. So this area here, this will have a height of A and a width of B minus A. So the area A times B minus A. Now, this area has a width of B minus A. We have a height of B minus A, because this is our B minus A to get this height. And right in here, it's B minus A. But this is a triangle, so it's going to be 1/2 base times height. So in here, the area, well, base times height are the same thing. It's B minus A. So we get B minus A squared. So 1/2 B minus A squared. So we just have to add these two areas up, and that's going to give us our area or our integral. So what this says is that the integral from A to B of x dx will be A B minus A plus 1/2 B minus A squared. And when you simplify this down, you'll get B squared over 2 minus A squared over 2. Now, you might look at this and you might say, well, okay, but when do we actually come up with some pretty slick formulas in this? And the truth is we won't be able to get to until we get to the fundamental theorem of calculus. And we'll finally be able to break out with all the formulas. And what we're going to find out is that what we did with antiderivatives in section 5.1 or 4.8, we can do that here. But we're not quite there yet. Any questions about this? All right. So similarly, we can show, and these I'm just going to put these out here. If we integrate a constant function like y equals c, we'll get c is b minus a for constant c. Also, we'll get b cubed over 3 minus a cubed over 3 if we try to integrate x squared. Now the thing to notice with this is we're not dealing with any plus constants anymore. Now we're not dealing with that. When we're dealing with definite integrals, there's no plus c like we did with antiderivatives or indefinite integral. So the last thing to mention in this section, the average value of a continuous function. So we looked at this a bit earlier, and what we came up with before that the average was approximately the estimate of the area, this is under some function f of x, over AB divided by b minus a. Or what this turned out to be was delta x. We had our f of c1 plus delta x times f of c2 and delta x f of cn. So we came up with this formula last time to come up for an estimate of the average value of a function. Well, what we're going to do better than an estimate. We're going to come up with a we're going to come up with a better average value is what we're looking for. And so we're going to replace, not with an approximation of the average, but we'll replace the estimate of the area over AB with the integral of f of x dx over AB. Where the average equals this. And again, we're using this as just a fancy expression for the area between the curve f of x and the x-axis between A and B. So for example, let's say we have f of x is equal to the square root of 4 minus x squared on -2 to 2. Now, what this is, we're looking at a half circle. And we're looking at the positive half. So what we have is this. And the reason we have the top part and not the bottom part also, if we had the bottom part, we would have the minus in front if we had the bottom part. But we have the positives. That means we have the top part. So what we need is the area of half a circle of radius 2. In that, I mean, we can use our formulas from geometry. So again, we're not using any special calculus formulas just yet. We'll get to that. We'll start talking about that in the next section. But for now, we'll try to solve these integrals. We'll compute these integrals using our formulas of geometry that tell us about areas, whether we're dealing with rectangles, triangles, or in this case, half a circle. So what we're going to find out is that the integral 4 minus x squared, we square root that, and that's a complicated integral. Well, we can, even though we don't have any formulas for something like this, we do know that it's going to be 1/2 pi r squared. This comes out to 2 pi. So what we can't do with calculus just yet, we can at least accomplish the same thing with geometry. So questions so far. Well, so the average, what's our integral? Over b minus a, or 2 pi over 2 minus -2. And that gets simplified down to pi over 2. So any questions about that? All right. So we're going to jump into the fundamental theorem of calculus. And again, for now, because of time constraints, I'm not going to go over the proofs. But if there were a couple proofs that I think would be just worthwhile doing, and you know what I might do? I might post a discussion on those separately, just so you have them. But it would be the fundamental theorems of calculus, because this is what's going to break open integrals for us. Because right now, to be honest, what we're doing with integrals, we're calculating integrals so far by using what we know from geometry. That's the best we can do. And that's pretty limited. You can do some creative stuff, but it's still kind of limited. So we're going to jump into the fundamental theorem of calculus. And this is the first one, episode 1. And this is what it says. For continuous f on AB. And this is where we're going to bring in our antiderivatives. This is going to be huge. then the integral, whatever number this turns out to be, from 0 to x, f of t dt. This is continuous. And differentiable on AB. And here we go. And the derivative of this sort of unusual function. So what we're doing, this function chooses x as the upper bound on the integral. It's using x as the upper bound of the integral. And then we just integrate. T is acting as what we call a dummy variable. It just lets us integrate f and then let x be a variable, so we have a variable upper bound. But here's where this is really cool. If you come up with something like this and you take its derivative, and you take the derivative with respect to x, and this is a bit of a trick here. You're taking the derivative when x is up here in the upper bound of an integral. Yeah, I might do a separate video for those of you interested, and I would recommend taking a look at it, the proof of the fundamental theorem of calculus. But the derivative of this thing gives you this. And then we're really going to break things open in episode 2. But we're not there yet. We got to watch episode 1. It's just the way it goes. So for example, if y is the integral, and it turns out, let me double check. Oh, I'm sorry, this doesn't have to be 0. This is a. My notes had that a little obscured. So real quick, before we go on, make sure this 0 is not a 0, it's an a. Which is, yeah, that's the way it should be. All right. So if we go a to x, t cubed plus 1 dt, then our f of x is going to be this function. Or f prime of x, we take the derivative, will be f of x. Because in here, this is our f of t. So now if we take the derivative, we swap t for x, we get x cubed plus 1. So questions about that? So we're breaking out of the stuff with this using geometry. We're now getting into something more tangible. Now, these can get a little tricky. You might say, well, this isn't too hard. I mean, that's your f of t. Get rid of everything, turn t's into x's, and we're fine. Well, they've got some tricky problems in here. Let me show you. And again, if I'm erasing too fast, let me know. I can always slow down. So let's say we have this. Now this one they could throw on homework problem. Two plus e to the t dt. And let me scoop this one over here so it's not so intrusive. There we go. Whew. Now that's a hoot. Well, what we can do, we've looked at this. We can let u equal 1 plus 3x squared. So u is actually acting like a variable. We won't know u until we know x. So to the extent that this is unknown, this is also going to be unknown. So we can write this as u up to 4 of 1 over 2 plus e to the t dt. Now, the thing here, though, is before we had the constant on the bottom and the variable on top, but clearly that's not what we have here. We got the constant on top, the variable on the bottom. So what we're going to do, we're going to reach back to those properties that say we can switch the order of the bounds. Make this the lower bound, make this the upper bound if we attach a negative sign. So now we have this. So we're getting closer. Now we're going to compute the derivative with respect to x, but we've got a u in here. So by the chain rule, dy dx will be dy du times du dx. Now dy du is going to be this integral, the derivative of this integral. So this will be d du of the integral from 4 to u 1 over 2 plus e to the t dt times du dx. Now this one, we're just going to use the fundamental theorem of calculus, episode 1. We may call it part 1, but we'll go with episode 1. So all that's going to do is clear everything out, leave f of t, but then replace the t with that variable. Oh, you're right. It does have a negative sign. Thank you. Thank you. Whew. It's going to have that negative sign. Thank you for catching that. You know, that negative sign, absolutely crucial. That's got to be there. All right. So what that's going to give us is negative 1 over 2 plus e to the u times du dx. And so du dx is going to be 1 plus e. Now u, we can replace u, put it back in there. It was 1 plus 3x squared times, and then du dx, well, it's going to be d dx of 1 plus 3x squared, because that's our u. And so putting it all together, we're going to get minus 6x over 2 plus e 1 plus 3x squared. Questions about that? So that's episode 1. Here's episode 2. And now we really open up integrals. So f is continuous on AB, where we're going to do our integral. F is capital F, antiderivative. So now we're talking about what we were looking at in section 4.8. The function that gave us a derivative. So here we go. If f is continuous on AB, and capital F is the antiderivative, then the integral, the definite integral of f of x, the area between f of x and the x-axis on AB is going to be this. This is going to be huge. This opens up the subject for us. So let me do a couple examples. There's a couple other topics in this section. I think we do have time to do them on Wednesday. Oh, wait, sorry. Oh, sorry. What part did I erase? Oh, this right here. Oh, I'm sorry. There you go. No problem. So we've slugged it out through a lot of theory. Now we've got something hands-on that we can do. This is going to be big for us. Is it okay if I erase? All right. Go ahead. So for example, the integral from 0 to pi cosine x dx. Now we recall the derivative of the sine of x is the cosine of x. So this means that the integral of the cosine of x dx, this will be the sine of pi minus the sine of 0, which is 0 minus 0, which is 0. Questions about that? All right. So let's say we're going to integrate x plus 1 dx, 0 to 1. Now we could play around with this a bit. And we're going to talk about something called substitutions on Wednesday that will make this problem a little easier. Because you might not recall this, but if we take the derivative of the natural log, absolute value of 1 plus x, and we do need, let's see, let me double check this example real quick. I think they should have some bounds on this. Let me just give me a moment. Make sure those are there. I didn't give any, but if you take the derivative, you'll get, oh no, you wouldn't need, you wouldn't want x being -1. You'd want to avoid that. But you're going to get this. And so what this is going to say, the integral of 1 over x plus 1 dx, well, that's going to be the natural log of 1 plus 1 minus the natural log 0 plus 1, or the natural log of 2 minus the natural log of 1. And the natural log of 1 is 0. The natural log of 2 minus 0, or the natural log of 2, and that's it. So that's gonna be it for today. What we're gonna do on Wednesday, we'll finish up a couple kind of points in section 5.4, and then we'll jump into 5.5 and 5.6, and then that's gonna be it. We'll be done with chapter 5. I'll get a pre-test out as soon as possible. I'll get the problems out first, and then I'll get the solutions second, and then I'll come up with a schedule for the exam. But if you have any questions, let me know. I'm going to do a couple adjustments with the homework. I'll get that done this afternoon. But if you have any questions, let me know. Other than that, have a wonderful day.
Hi, Professor Coburn.
Hi.
So is today the last day